Okay, chapter 12. Chapter 12 is called the test of goodness of fit and independence. So this is chapter 12. And we are going to deal with not anymore with population parameters, hypothesis testing about population parameters. We are going to deal this chapter about hypothesis testing about how well the data that we have fits a particular probability distribution. The other thing is the independence, test of independence, and we are going to test if two variables are independent from each other. Okay, that's it. And we are going to use the chi-squared probability distribution in order to make the decision about the whether we reject or do not reject the null hypothesis. Okay, let's start with the goodness of fit. And we're going to start with one particular probability distribution where we know what are the probabilities of each one of the categories. So we have category 1, A, B, C, or whatever the number of categories, and we are going to have what is the probability of that particular category, and of course, if we add these probabilities, it has to be equal to 1, okay? We are going to have an observed value, or the observed number of elements in each one of the categories, okay? And we are going to have the expected number of elements, and in this case, the expected number of elements would be the total sample size times these probabilities. And then at the end, we are going to add what? The observed, or in this case, are the frequencies observed minus the expected on each particular category squared divided by the expected number. And we are going to add for each one of the possible categories. And then we are going to compare, and this is always going to be an upper tail test, chi-squared, with how many degrees of freedom? In this case, we're going to have the number of categories is going to be k minus 1. Okay, so it's the number of categories minus 1, and we are going to compare this value. This is the test value, okay? And we are going to compare this test value with the chi-squared, where if we are going to use alpha over here, this is my critical value, such that if this test value is in the rejection zone, we reject. What? The null hypothesis and the alternative hypothesis. The null hypothesis said that it fits. The alternative, it doesn't fit. Okay? So that is why it's not anymore equal or greater or less or whatever. We are dealing with it fits this particular distribution, or it doesn't fit the particular distribution. So this is it. That's it. Simple. It may be some calculations, but it's straightforward. Okay, let's do one example, one problem. Let's do problem. Let's do problem number 8. Number 8 is on page. Oh my goodness. On page 479. Okay. So the problem says, how well do airline companies serve their customers? A study show the following customer rating. 3% is excellent. So let me write it down. We have excellent. We have good, fair, and poor. Okay? In this case, we have 4 categories. Okay, the probabilities, they are giving us the probabilities. And they said for excellent is 3% or is 0.03. Good is 28.28. Fair is 0.45. And poor is 0.24. If we add these numbers over here, it has to be equal to 1.0. Okay? What else? In a follow-up study of service by telephone companies, assumed that the sample of 400 adults, so we have adults, N is equal to 400. 400 adults found the following customer rating. 25, okay, this is the observed. This is what the observed said. We have 24 excellent, 124 good, 172 fair, and 80 poor. If we add this number, this is equal to 400. This is the number of total sample that we have, if you will. Is the distribution of the customer rating for telephone companies different from the distribution of customer rating for airline companies? This is the probabilities of the airline companies, and we want to know if the telephone service is different from the airline companies, and they said alpha is equal to 0.1. Okay, so we know that we have to test using a high-square distribution with how many degrees of freedom? The number of categories minus 1. We have 4 categories, so it's 3 degrees of freedom. And they said 0.01, the distribution, so go to the table, high-square table with n minus 1 degrees of freedom, 3 degrees of freedom. 0.01 is equal 11.345. So this is 11.345 is my critical value that is going to divide the rejection zone from the non-rejection or do not reject zones. Okay, so first we need to calculate the expected number of elements of these 400 if they follow this distribution, and that's nothing but n times the probability. So we have 400 times 0.03 is equal to 12 times 0.28 is equal to 112 times 0.45 180 and 0.24 is equal to 96. If I add this, of course, has to be equal to 400. Okay? Now, let me erase this because we know that is 400. In order to calculate the test value, it says that it has to be equal to the summation of the frequencies minus the expected square divided by the, the summation of the frequency minus expected square divided by expected of each one of the categories from category 1 to 4 for each one of the categories. We have the frequencies over here that are the frequencies over here that is the observed. This is the expected, okay? And what we need to do, nothing is but do the math. So I'm going to do just a few. Its frequencies, 24 minus 12 squared divided by 12 plus frequencies 124 minus 112 squared divided by 112 plus 172 minus 180 squared divided by 180, and so on and so on and so on. And this is equal, I already did this, is equal to 16.31. Okay, so let me write it down in here. This 24 minus 12 squared divided by 12, this is 12. Okay, this is the frequency minus expected squared divided by expected. This is 12, this is 1.2, I have it in here, 2857, this is 0.355, and this is 2.666. And the total over here is equal to 16.31, and this is my test value. I'm going to compare this test value, okay, with the critical value over here. And this 16.31 is here, is in the rejection zone. So the conclusion of what is the hypothesis? It fits, and the alternative doesn't fit. So we reject. This is in the rejection zone. What we reject the null hypothesis. So we are going to say that the alternative hypothesis is correct, so it doesn't fit. So these data, or the customers from the telephone company, do not follow the same distribution for the airline customers. It doesn't fit. They are not equal. Okay? And that is the conclusion, pretty straightforward.